Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and I have our fourth video in a series on sequences. And today we're going to be talking about recursive rules for sequences. In the previous lessons on sequences, we've talked about general sequences, arithmetic sequences, and geometric sequences. We've written rules for those sequences, but we've written what are called explicit rules. When we can write explicit rules, they are certainly more useful than what are called recursive rules. Recursion is a process where you keep repeating a process over and over, and the results of the next step depends on the results of the previous step. So we keep modifying the previous step in some way. These rules are easier to write because if we can discover the pattern in the numbers, then the rule is essentially the mathematical representation of that pattern. However, they're not as useful as the explicit rules, especially when we're trying to find a term far out in the sequence. With an explicit rule, we could calculate the 100th term in a sequence directly. For a recursive rule, we would have to find the first term, the second term, the third term, all the way up to the 100th term. We can't just jump ahead. So it makes it not particularly useful for lengthy sequences. So let's look at the notation. So for a recursive rule for a sequence, you're going to have two items. We have to specify at least the first item in the sequence where it starts. For some recursive sequences, it may give you the first 1, 2, or 3 items in the sequence. And then we have a rule, and we use the subscript notation. So a sub n minus 1 is the mathematical way of saying the previous term. So in this example, we are taking the number of the term times the previous term. So to write out the first 4 terms of this sequence, so to write the first term, we're already given that was given. And to write the second term, so now n is 2, we're going to multiply that number, 2, times a sub n minus 1, which is the previous number. To write the third term, we are going to take the n value, which is now 3, times the previous number. And finally, the fourth term will be the n times the previous number. And we could list these this way, or we could list out the sequence that we are forming. So in this next example, we will be adding n to the previous number. So the first item will be 5. Now this was n equals 1, so n equals 2. We're going to be adding 2 to the previous number. Now we're going to be adding 3 to the previous number and 4 to the previous number. So each time we're adding 1 more because the n keeps stepping up by 1. On our third example, we'll be multiplying the previous number by -5. So this is the recursive formula of a geometric sequence, because if you remember from geometric sequences, we have a common ratio or a common multiplier. So in a geometric sequence, this would be r. This is the way we would write the formula for a geometric sequence in recursive form. So a sub 1 was -0.8, and we're just going to keep multiplying by -5. So -5 times -0.8 is +4. Multiply that times -5, multiply that times -5. And we could keep repeating that process. And finally, our last example here, we'll just fill in the formulas. So we've got 2 plus the previous term divided by 2. So that's -28 divided by 2 is -14. We could also simplify this and divide out, so we get 1 plus the previous number divided by 2. So we can take the previous number and add 1, the previous number and divide by 2. So when we get a sub 3, we could take this, divide by 2, and add 1, and we would get negative 6, or we can just plug into our formula here. Gives me negative 6, and the fourth term would be half of that plus 1, negative 2. Now in our next example, we're going to want to find the nth term. Now in this case, you'll see it's going to be a little bit more tedious because we need to just keep repeating that. So here we're adding n to the previous term, so we're adding 2 to this, we get 3. Now we're adding 3. Now we're adding 4, adding 5, adding 6, adding 7, adding 8, 9, and 10. So you can see we had to go, it's a 10 there, we had to go through the list. Now we could do the same thing here, or as I mentioned before, when we have a common multiplier, this is a geometric sequence. So instead of writing them out like we did here, I'm going to write the explicit formula. Now the explicit formula for a geometric sequence, if you remember from our earlier lesson, is this template. So our a sub n would be a sub 1, which was given to us, times r, which is the negative 5, to the n minus 1. So now this is the recursive formula, and this is the explicit formula. So if I want to find the 10th entry, we can just calculate here that number, and I've used a calculator previously to compute that, and you get 390,625. So now we have demonstrated using recursive notation. So now let's try to write some recursive rules ourselves. So first thing we need to do is we need to try to look at the pattern. So in this case, we have added 1, added 3. So adding doesn't seem to have a pattern. So let's look at another pattern. We could see here that going from here to here, we're times by 2, times by 3, times by 4, times by 5. So this was the second term, and we multiply by 2, multiply by 3. So we are multiplying the previous term by n. So now we can write the explicit recursive rule. So a sub 1 is 1. And a sub n is the previous number times n. So that's our recursive formula here. Here we are adding 9. Adding 9. So it looks like we are just adding 9. So the recursive rule would be a sub 1 equals 5. And to get the next term, a sub n, we are going to take the previous term plus 9. Now this is also this is an arithmetic sequence, and we also know how to write the explicit formula for that. I won't go through that since this lesson we're talking about recursive rules. All right, let's look at our third example on writing rules, and let's see if we can see the pattern. So here we're plus 2, plus 3, plus 4. So we are plus 2, and this is n2, so we're adding n. So we have a sub 1 equals 2, and a sub n equals the previous term plus n. So in this case, we added a constant number, and here we were adding a different number each time, but that number that we were adding related to what term we were in the list. Just takes some experience here to discover these patterns, but you can see from the examples we've done so far, once you discover that pattern, writing the rule is quite straightforward. And our last one here, you can see we are constantly multiplying by 3. So this is a geometric sequence. And our recursive formula for that, again, would be a sub 1. And our next term would be the previous term times 3. There's a special sequence that I'm sure you've heard about in your mathematical career referred to as the Fibonacci sequence. So a mathematician named Fibonacci discovered this sequence in the year 1202, and he was studying the pattern of the reproduction of rabbits and looking at a mathematical way of representing the growth of that population. If you take the ratios of adjacent numbers in a Fibonacci sequence, this was discovered later, you get approximately the same number when you take each ratio, and it approximates a number, a Greek number called phi, which is also called the golden ratio. Golden ratios are used frequently in art and architecture when doing perspectives or proportions of pictures. It's shown to be very appealing to the eye. And also people have studied and found Fibonacci number sequences in nature and looking at the way the spirals on a shell grow or the way the petals on a sunflower flower are arranged and the bumps on the surface of a pineapple. So let's look at this sequence. And in this sequence, the pattern on the Fibonacci sequence is a number. The first two numbers are 1, but after that, each number is the sum of the previous two numbers. So 3 is the sum of 2 plus 1, 5 is the sum here. So to write that as a recursive rule, we have to specify both the first two terms, and then we can specify the nth term as being the previous term plus the one previous to that, which would be n minus 2. And this would be the recursive definition for a Fibonacci sequence. I don't remember, it's certainly very difficult to write an explicit rule for the Fibonacci sequence, and I don't remember whether there is a mathematical formula for the explicit sequence or not, but it certainly would be very difficult to write. So I hope this helps with looking at recursive rules, and we'll see you around.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you